hear me okay without it? Okay, awesome. Yeah, thank you so much for filling the time with that beautiful introduction. I will be telling you things that involve many squiggles and exchanging many orders of limits and doing many illegal things, all with the goal here of just trying to convey the high-level ideas. Which one? This one, sorry. The other one. We good? I'm tangled up in cords. Okay, so before I get into any of the details here, let me just take a quick second to acknowledge my many excellent collaborators, without whose efforts none of the work I'm going to be telling you about would be at all possible. So many people from Google Brain, where I am, from Stanford, Microsoft. I'd like to especially acknowledge Sam Schoenholtz, who contributed a lot of content to these slides. So as a brief outline of what I'll talk about today, first I'll try to give you a high-level motivation both from the microphone is not working. I don't know. So many things.
Let's check that it works.
Is it working?
No. Now it's green. Maybe it's working.
Now? Hello?
This is the one we had before.
Okay. Yeah, third time is the charm, hopefully. I'm completely tangled up here. Okay, so yes, so I'll begin with the motivation for why I think studying over-parameterized networks is interesting both from the practical perspective and also from the theoretical perspective. In many ways, especially in the sense that it can enable us to actually exactly characterize the distribution over functions that the neural network defines that's induced by the randomness in the initial parameters. And I'll talk a little bit about these functional priors defined by very large neural networks. And in particular, I'll try to characterize some of the ways that those priors can become pathological as the depth of the network becomes large, and hopefully introduce some tools and methodologies for selecting hyperparameters in order to kind of prevent the onset of those pathologies. And hopefully I'll have time by the end to try to move beyond the prior distribution over functions for over-parameterized neural networks to actually say a few things about the distribution of functions after training, the posterior distribution. And by that I mean, concretely, if you take an ensemble of neural networks with initial parameters drawn from some initial distribution, and you evolve each member of that ensemble with gradient descent, then what is the distribution of learned functions that you find at the end of the day? Okay, so this is the basic outline. And let me start with a pretty high-level abstract motivation, I think, for why I think it's a good idea to study over-parameterized neural nets. And the motivation comes from statistical mechanics and thermodynamics. And I think it's probably very familiar to many of you. But let me just try to say what I mean in a bit of detail here. So suppose you're interested in characterizing the properties of some physical system. Say, for concreteness, that we want to talk about the properties of, say, the air in the room. Well, from at least from the perspective of classical mechanics, should I turn this off? Okay. Sorry about all of that. Yes, so from the perspective of classical mechanics, the way to characterize the properties of this system would be to specify the position and momentum of each of, say, the n particles. And furthermore, if you were able to somehow measure or knew a priori what those kind of microscopic degrees of freedoms were at some time, and you knew the Hamiltonian of the system, then in principle, you could derive a set of coupled differential equations that would govern the time evolution of all of these degrees of freedom. And if n is relatively small, like 1 or 2, then it's possible to solve those differential equations exactly and come up with an analytic characterization of the time dependence of the fundamental degrees of freedom. When n is maybe slightly larger than that, you can probably solve those equations numerically to high precision and get a good estimate for what's happening. But when n is very large enough to describe a macroscopic system that maybe people would care about, those techniques are basically impossible. So what do you do? I'm sure you all know the answer here, but when the number of interacting particles is huge, then instead of trying to discuss the system in terms of its microscopic degrees of freedom, it becomes more natural and effective to try to characterize the properties at a macroscopic level. So to discuss, instead of the individual particles, to discuss some macroscopic observables like the pressure, the temperature, the volume of a system. And instead of having 2n, very large number of degrees of freedom, now you're only talking about some finite, small number of properties that you care about. And in many cases, for example, in equilibrium, those quantities are related to one another in a very simple way. So I'm not saying that it's necessarily easy to derive what these quantities are or to infer their relationships. But nevertheless, the existence of them, I think, is a strong motivation for trying to come up with a simple observables to describe the behavior of systems that contain a large number of interacting degrees of freedom. So obviously, what I'm leading up to here is that neural networks are systems with a large number of interacting degrees of freedom. And probably the way that you normally think about a neural net is on the microscopic scale, where you have some maybe large number of neurons, and between each of them, you have some weights connecting. And well, the fundamental degrees of freedom are, of course, the parameters in the model, the weights and the biases through each of the L layers and neurons in a given layer. The collective set of parameters theta really characterizes what's happening. And of course, we know how the parameters theta evolve. Typically, they would evolve through, say, gradient descent. But simply being able to specify the equations for the dynamics and to understand what the microscopic degrees of freedom are isn't really sufficient to characterize the essence of what's happening. Like, there's complicated phenomena that just are not apparent by studying the microscopic degrees of freedom. So the question is, if we take the, for example, hidden layer to be large, what is the macroscopic picture that emerges in the context of neural nets? And I would say that this is still an open question. So part of this motivation is to encourage people to think about this question. I'll give you my perspectives on parts of the answer, I think. And one way, though, I would like to try to characterize the macroscopic picture of the neural net is kind of in this skeleton of the neural net architecture, where the rectangles I've sort of purposefully left empty to denote there's some ambiguity in what one might put there. But for example, you could imagine the rectangle as encoding a distribution over the values of the neurons at a given layer rather than their individual values. And the arrows now are implying some kind of transformation that happens between the layers rather than a dense connection of weights. And so another important question, though, is like, what are the macroscopic observables that one cares about in a neural network? What's the analog of the temperature, for example, or the pressure, or the volume in these kinds of systems? And I would say, again, that as a community, we don't really have a concrete answer to this question. But I'm going to be talking about one possible set of observables today that I think is particularly salient. And that is the set of per layer covariance matrices sigma. So here, I is an index that runs over the neurons. X is the representation at layer L, and A and B are sample indices. So sigma L is the sample-sample covariance at layer L. And even when n becomes large, sigma is still a relatively simple object. And in fact, when n becomes large, it may even be simpler than when n is small. So I'm going to be talking, there could be other macroscopic objects that characterize properties of neural nets that are interesting. And I would also like to say that, we don't necessarily know how these macroscopic objects relate to one another, but hopefully we will be able to derive certain kinds of relationships. I think one relationship that we know to hold in some contexts is that these covariance matrices don't really change during the course of gradient descent under some conditions as the width becomes very large. OK, so this is just a high-level perspective on kind of one of the goals, I think, in studying over-parametrized models from the theoretical perspective, is that a lot of simplification can occur, and maybe some insights into the right types of objects to think about could emerge. But of course, if it were only this, I'm not sure over-parametrized networks would be the study of such a large amount of study. The other side of the story is, of course, that they tend to perform much better. So I'll just give a couple examples of this. On the left panel here is a scatter plot of the generalization gap for a wide array of different models with different hyperparameter configurations and different numbers of weights along the x-axis. And you'll see the prominent pattern here being some kind of vertical lines. So for each vertical line, that's a collection of models with the same number of weights with different hyperparameters. The different hyperparameters induce different performance. But if you look at the best performing hyperparameter configuration, like the bottom of each vertical line, you see a downward trend as you increase the number of weights. Like the best performing model is typically better as you increase the number of parameters. OK, so in the convolutional context, you also see something similar. As you increase the number of channels in the convolutional kernel, the accuracy goes up. For residual networks, you see similar behavior. The test error goes down when you increase the number of parameters. So this is by now a pretty well-known phenomenon. So I would just leave it at that. I would say I think there's strong theoretical reasons and pretty strong practical reasons to be considering networks of this type. OK, so with that motivation, now let me try to turn to a slightly more specific characterization of the kinds of things that one can actually say about some of these macroscopic observables, quantities of these very large over-parametrized neural nets. So to begin, let me start with a result from now 25 years ago from Radford Neal that specifies the prior over functions that's induced by randomly initialized single hidden layer neural nets. So to set the stage, I will be considering inputs denoted by x, with A and B denoting the sample index. Well, I'll call sigma 0 the data second moment matrix, or actually, usually things will have 0 mean, so this is sort of the data covariance matrix. The parameters to the model, W and B, will be drawn from a Gaussian distribution with variances sigma W squared and sigma B squared. And importantly, actually the variance for the weights is scaled like 1 over the previous layer width in order that the first layer pre-activations, Z, are order 1. And so, just the standard definition of the simplest possible neural net here, you have the pre-activation Z. It's just an affine transformation of the data. And the output of the network Y is an affine transformation of a nonlinear function phi applied to Z. Okay, so I haven't said anything yet. What I will say, though, is very trivial. Z is a weighted sum of Gaussian random variables. And so these pre-activations are jointly Gaussian. And that's because the W1 are drawn from a Gaussian prior. And then the other trivial thing I'll say is that because the number of hidden units in the first layer, N1, is going to be taken to be large, going to infinity, then the outputs Y are a sum of a large number of IID random variables. And so they, too, become distributed as a Gaussian with some covariance, sigma 2, I'll call it. Okay, so this is a result that's been known for a long time, and actually I've more or less proved the main point, which is that infinitely wide neural nets for a single layer are Gaussian processes. To say the result slightly more specifically, we showed, in essence, that for every finite collection of data points, the outputs of the model are jointly Gaussian. So infinitely wide neural net of a single layer is a Gaussian process. But the interesting part here, I think, is that the kernel of this Gaussian process, the covariance function sigma 2, is actually really simple. And it's defined kind of recursively with a simple structure. So first, one computes the covariance of the pre-activation Z1. So if you basically look at this top first equation and sort of square it, then it's easy to see that sigma 1 is just the weight variance times the data covariance, sigma 0, shifted by the bias variance. And then if you just do the same thing for the equation for Y, you basically get the same answer, except instead of the data covariance, you get the covariance of the post-activations. So the covariance 5Z. And, well, this object itself is quite simple because Z is a Gaussian random variable, and you know the covariance. So, in general, you can evaluate that expectation numerically. And for certain activation functions like error function or ReLU, for example, you could evaluate it analytically. And OK, so for those of you who maybe haven't thought much about Gaussian processes lately, just to say one thing and give an example. So Gaussian process is a distribution over functions. So a sample from the Gaussian process is itself a function. And what do those functions look like? Well, here's some samples in the 1D case. These are draws from a neural net Gaussian process, single hidden layer with activation function ReLU. Each color is a different draw from this Gaussian process, and this is what they look like. Okay, so this is all very old. Newer result, although not much less trivial, but a newer result is this extension to deep networks. So how does this work? Well, basically, it's exactly the same thing I just described. So in fact, identical to the previous slide, we have the covariance on the first layer pre-activations is given by this expression for sigma 1. And then you can, at the microscopic level, iterate the forward pass of a single layer of a fully connected neural net. And that gives you Z2, the second layer pre-activation units. In fact, Z2 is just another way of labeling the quantity I called Y in the previous slide. And the same reasoning applies here, that sigma 2 is given as this function of sigma 1. But when I say it this way, that sigma 2 is a function of sigma 1, I mean, what is that function? That's just some function. We'll call it the covariance map C. So basically what this picture is illustrating is on the left-hand side some kind of microscopic operations at the level of the individual neurons and parameters. And on the right-hand side, that operation lifts to some kind of simpler operation that acts in the space of these macroscopic objects, these covariance matrices. And of course, one can just iterate this many times. And by layer L, we have some pre-activation unit ZL, which one can consider the output of the network, and correspondingly some covariance kernel, sigma L, that completely characterizes the Gaussian process that defines the prior distribution over functions of this deep, fully connected feed-forward neural net. We call this, for that reason, the neural network Gaussian process kernel. So again, if we can understand the properties of sigma L, we'll understand the prior distribution over functions that the neural net defines. And so the name of the game here is to understand what happens when you iterate the application of this covariance map C. And the perspective we're going to take is that in the space of covariance matrices, the evolution of sigma is just a dynamical system. And the propagation of sigma through this dynamical system is just what we call signal propagation, signal being the information in these kernels. OK, so we have this dynamical system. And it turns out that, yeah.
So when you say that the neural network is a Gaussian process, it seems like you're saying something about the distribution of the output, but not the relation that might exist between the input and the output. Is that correct? Is there, like, are you saying something about the function that is learned, or only about the distribution of the output?
The function. The function itself is a draw from a Gaussian process, which is basically an object for which any finite collection of input points are jointly Gaussian. So I mean, maybe if I pull up this picture again. So each of these lines is a draw from the Gaussian process. And you can think of this graph as defining the function. So for each value on the x-axis, that's an input. And the output is the value of the neural net for that input.
This input here is one-dimensional?
In this case, just for visualization.
The output is like multi-dimensional for 2025?
No, the output is one-dimensional in this case too. Each line here is a different sample from the distribution over functions.
So sorry, can you come back just a second to that slide? So here you were talking about y IA times y JB, and this is Gaussian. So it seems like there's no input here, it's just y, it's just the output.
Sigma 2 depends on sigma 1, which depends on sigma 0. Sigma 0 is the covariance of the data itself. I mean, I think that's a fantastic question at finite width. And maybe that's, in fact, a good way to pursue the finite width corrections in terms of some Hermite expansion, although I haven't been able to figure out how to do that for more than one hidden layer. I think for infinite width, though, the information content will be the same. It sort of has to be the same, because the only information that exists is that which is encoded in the covariance kernel of the GP. So if you did manage to do some Hermite expansion, I don't know how it would play out, but somehow.
So you said in your notion of covariance kernel, you include covariances of entries at two different layers.
Right. So right. So I was trying to brush this point under the rug, but but no, you bring a good point here, and the point is with regard to the order of limits, essentially. So the assumption that I made in this particular way of presenting things is that the limit of the first hidden layer going to infinity happens first, and then the second hidden layer, and the third hidden layer, et cetera. And when you do that, then I believe it's consistent to regard the covariance as only talking about that with neurons within a given layer, because it's independent of the others. It turns out, though, that the Gaussian process kernel that you get by considering a joint limit is the same, although technically that's much harder to show. Right, where was I? Yes, so in order to understand this prior over functions that the neural net defines, one needs to understand the behavior of iterating this covariance map. And it turns out that for most architectures that are sort of standard, for example, fully connected feed-forward models, convolutional feed-forward models, and a variety of other things, that the repeated iteration of this covariance map will converge to some fixed point, sigma star. And actually, this is a universal fixed point in the sense that the values of that matrix don't depend on sigma 0. They don't depend on the data at all. And obviously, this is pathological. The prior over functions that would define would be some constant functions. And this is just a terrible situation for learning anything. So if the fixed point covariance is pathological, the question here is, how does one understand the convergence to that fixed point, how close you are to that pathology for some finite depth? And to do this, we just use this sort of standard tools you would use in studying any dynamical system and its convergence rate by expanding around the fixed point. So we look at the residuals epsilon that are just sigma star minus sigma L and ask how those residuals propagate from layer to layer, which is equivalent to just looking at the sort of first order Taylor expansion of this covariance map C. In fact, epsilon at layer L plus 1 is related to epsilon at layer L by means of the multiplication of the Jacobian of this covariance map evaluated at the fixed point. So to know whether and how quickly epsilon is changing, you need to know how big this Jacobian is. Or slightly more precisely, whether its maximum eigenvalue is bigger than 1, in which case the epsilons are going to get bigger from layer to layer. And in fact, you're going to diverge from the fixed point. Or if the maximum eigenvalue is less than 1, then the epsilons are going to get smaller from layer to layer, and you're going to converge to it. So sort of heuristically, neglecting the vectorial structure here, the residual at layer L is roughly the maximum eigenvalue to the L power. That is to say, you have exponential convergence to the fixed point. And the depth scale over which you expect that convergence to occur is this quantity xi, which is -1 over the log of the maximum eigenvalue. So you sort of have a characteristic depth scale that says through how many layers you expect the signal from the input to persist in this deep feed-forward neural net. And you want that to be as large as possible if your goal is to train a deep model. And so if that's your goal, how can you adjust the hyperparameters to achieve that goal? So to answer that, you need to know slightly more about the structure of the fixed point. So in fact, we don't have totally general results characterizing all of the possible fixed points. But we don't really need them because there's one fixed point that's totally obvious, and we can expand around that. And that fixed point is the one where sigma star is just a constant matrix, which basically means that every sample is perfectly correlated. It's the same vector, in fact. You pass two samples through the network, and at the fixed point, they'll become the identical vector. And obviously, if that's occurred, you apply one more layer of the network, the two representations will remain the same. So if you iterate one step of the covariance map, then the fixed point is, sigma star will not change if it has this form. So this is one solution to the fixed point equation. And what we want to know is if it's stable. Is the maximum eigenvalue bigger or less than 1 for this fixed point? And of course, the answer to that depends on the hyperparameters. So what you can do is characterize the stability of the fixed point in the hyperparameter space. In this case, it's a plane with sigma w squared and sigma b squared. And that plane fills out a kind of phase diagram, where on one side you have a stable fixed point and the other side an unstable fixed point. And the gross structure, I think, of this phase diagram should be pretty intuitive for the following reason. If you're on the left-hand side, then the bias variance is large relative to the weight variance, which means that at each layer, to every sample, you're adding the same fixed bias vector. That bias vector is independent of the input, and it just serves to increasingly correlate the samples as they move from layer to layer. So the correlations increase in depth if the bias variance is big. And so I think that sort of gives an intuitive explanation of why on the left-hand side of this diagram, the fixed point will be stable. And we call it the ordered phase because basically all the points converge to the same representation.
Did you actually check empirically that you get this matrix that you showed there?
Yeah.
And it happens?
Indeed, yeah.
Always?
No, it doesn't happen always. But there exists points in the phase diagram for which it does happen, and we're analyzing the stability of those points. And in fact, you converge to a different fixed point if you're on the other side of this phase diagram. And that's because as you move from left to right, the stability of the fixed point sort of decreases, i.e. lambda max gets larger and larger. As it passes 1, you cross this phase boundary. This sigma star equals constant matrix fixed point becomes unstable. And instead of converging to that fixed point, you converge to a different one.
And what's the difference?
Different one is basically a matrix with some constant on the diagonal and some different constant on every off diagonal. And of course, as you transition across this phase boundary, lambda max equals 1 as you are on the line. And if you recall the definition of this depth scale xc, -1 over log lambda max, you see that the depth scale diverges, which is maybe exactly what you want, which is you want to be able to persist information about the input arbitrarily far through the network. So to say another way, if you want to have your signals propagate through deep networks, you want to initialize right on this critical line, what we call the edge of chaos. And in order to do that, we want to examine the details of this fixed point, this constant sigma star matrix fixed point, and at that fixed point, set lambda max equals 1. So this actually requires you to evaluate the Jacobian at this fixed point and compute its maximum eigenvalue, which you can do. It's some function chi, depends on the hyperparameters. And for the simple feed-forward fully connected architecture, the expression is pretty simple. It's just basically the Gaussian expectation of the square of the derivative of the activation function.
Sorry. So in one case, you converge to a matrix of ones, and that's in the Gaussian part. In the other part, you converge to a matrix which is diagonal plus sum of diagonal. What happens exactly on the edge of chaos?
It's ones. It's all one everywhere. Yes. OK. So the point here is that you have an explicit expression for this quantity chi, which you can set equal to 1 by adjusting the hyperparameters of the model. Okay, let me just take a brief aside sort of to talk about the dual perspective to the forward propagation of signal, which is backward propagation. And this is actually quite a bit simpler to talk about. So suppose you have some loss function L. You know that the gradient of that loss with respect to the weights is the outer product of some backpropagated error signal delta with the post-activation vector 5z at the previous layer. The backpropagated error signal delta itself is the gradient of the loss with respect to the pre-activation z. And the deltas are related to one another through the standard backpropagation recursion relation. So if you just compute the sort of the scale of delta, i.e., kind of the variance of both sides of the upper right equation, you get a relationship between sort of the scale of delta at layer L to that at layer L plus 1. And the relation is multiplicative by a factor that's exactly this quantity chi that I put on the previous slide. And if you iterate this recursion all the way down to the bottom of the network, looking at how the error signals change as they move all the way through the network, they get scaled by chi to the L. So you get exponential explosion or vanishing of your error signal unless chi equals 1, which of course is the same relation I argued for in terms of forward propagation. And we can fill out this phase diagram with some additional labels. And the ordered phase, you have vanishing gradients, and the chaotic exploding gradients. And on the phase boundary, the gradients do neither. And if you choose the hyperparameters to live on this critical line, this phase boundary, you get what we call the critical initialization. And the hope is that this would allow you to train very deep models. So this is one prediction of our analysis. But in fact, it's not the only prediction. Because we have a more quantitative analysis we can do by evaluating our predicted depth scale of trainability at arbitrary points in the phase diagram. So for concreteness, let's say we take some value of the bias variance, a small one, say 0.01. And for each of those weight variance along the dotted green line, we compute this Jacobian and its maximum eigenvalue and therefore this depth scale as a function of sigma w. So that's something we can do. And then you can plot the result in this dashed line on the left side. And the left side is showing the training accuracy at some time on MNIST. The dark pixels are 0 accuracy. The bright red ones are 100%. And the y-axis here is depth. So each pixel represents a particular model that we trained. And let's see if this works. Yes. So as you evolve the system with gradient descent, more and more of these models are getting high accuracy. And at late time, you see that the shape of the contour of the trainable region is very well modeled by our predicted trainable depth scale. So the point here is that there's a lot of predictive power just by analyzing the prior over functions. You can also do the same thing for convolutional networks, similar heat maps on the right. On the left-hand side, we push the depth to 4,000. Here we see the convergence is slower. This is 100,000 steps. But you can see it's going up, even for a depth 4,000 CNN. So each pixel represents the accuracy at some time. There are 4 different time slices in the 4 different panels. The y-axis is the depth of a model we trained, and the x-axis is a value of the weight variance. So each pixel is a different model we trained, and the intensity of the pixel is the accuracy that we got after this amount of time training. That's sort of whether or not you can achieve better than chance accuracy training with gradient descent, essentially. So you could, for example, ask what's the training accuracy at late time. And if it's significantly above chance, then maybe you can train. Yeah, it's not a very precisely defined quantity.
Maybe I missed this. Do we know that there's only a unique fixed point, or there are multiple fixed points, and how does the distribution of fixed point actually depend on your hyperparameter?
It's basically unknown.
So for the type of deep models that you're considering, usually people apply some sort of normalization, batch norm, layer norm. Does this analysis, kind of describe what's happening there?
The short answer is yes. The long answer is that batch norm is extremely complicated. I can talk to you about it offline. The results are very complicated. But the upshot is that it seems like gradient explosion is inevitable with batch normalization. So it makes things worse.
Gradient explosion is not a real problem because you can always normalize the gradient and then move a few steps. And after a few steps, the conditions that you have in your maximums, i.e. the distributions and matrices are not valid.
A totally valid point. After one step of training with batch norm, even though the gradients explode, because of the normalization layer, you can continue to train because the output of the function is not diverging. And in fact, that is what seems to happen. So there's lots of effects. But I would challenge you to use some heuristics to train 10,000 layer fully connected feed-forward model without tuning the hyperparameters like this.
So it would be pretty interesting to overlay like a generalization heat map on top of trainability. Do you have any insights on what that might look like?
Yeah, we have a paper coming out about that. Yeah. There are some differences, but it's pretty subtle. Yeah. Okay. Let's see. How am I doing here? Okay. Let me quickly go through a nuance that I'd like to add on top of this perspective of the distribution over functions that I've been putting forward so far, which is to consider not just the output of the model Z, but its gradient with respect to the inputs. So this end-to-end Jacobian matrix, which in the context of feed-forward neural nets decomposes into a product over layers of the per layer Jacobians. Each per layer Jacobian itself decomposes into the product of a diagonal matrix and a weight matrix, with the entries of D being the derivative of the activation function. This is just standard chain rule. Why do we care about the Jacobian? A number of reasons. With respect to the exploding or vanishing of gradients, I argued in a just slightly different language that the backpropagation of delta is governed by a multiplication with J. Of course, the dual to that is that the Jacobian dictates how a network will respond to small perturbations of the input. And if you view the neural net as sort of defining an embedding in Euclidean space, the metric on that submanifold is induced by the Jacobian. So this is an interesting object. And it relates to what I talked about in terms of vanishing gradients in the following way. If the mean squared singular value of J, or the trace of J transpose J, the same thing, equals 1, then you'll satisfy the criticality condition that I described previously. So there's a condition you can impose on the spectrum of J that gives you criticality. But the question is, what is the appropriate prior for the entire spectrum? And I would argue that isometry is a good prior here. So not just that the mean squared singular value is 1, but that all the singular values are pretty close to 1. So that it's not just that the gradients don't explode on average, but that there are no error signals that will get amplified or diminished by a large amount as they backpropagate through the network. Okay, so how can you ensure this? I won't have time to go through the details here, but you can use some nice tools from random matrix theory in this infinite width limit to actually get an analytic formula for the spectrum for the Jacobian. And with that analytic formula, you can sort of interrogate it and ask, what can I do to ensure that the spectrum becomes concentrated around 1? And here's just a caricature of those results. Basically, if you use a Gaussian weight matrix or any activation function, the density of singular values, i.e. the probability of getting a singular value, any particular singular value sigma, it has this shape where it concentrates around 0, and then there's some large outliers. So the mean squared singular value can be 1, but it's highly skewed. You could try to fix this with orthogonal weights, but if you do that with ReLU, or if you do that with a sigmoidal activation function like tanh, and the weight variance is too big, then you'll fall into the same problem. But if you sort of do all three things, you're orthogonal, you have a activation function that's sort of linear about the origin, and you use a smallish weight variance that's close to 1, then you can get this behavior that we call dynamical isometry. Okay, that's just like a lightning characterization of how this works. And what happens in terms of the phase diagram, basically it means you want to choose not just any point on this critical line, but some special points that are kind of now near the left edge, and use orthogonal. So what happens when you do this? Here's the plot I showed before with critical init. If you do also this dynamical isometry, you get orders of magnitude training speed up. And you can go even farther. So we push this to 10,000. I mean, I think you can just go arbitrarily far, essentially. Yeah, so I'm analyzing the prior over functions. One of the ways that I add some nuance to that analysis is to examine the Jacobian matrix. It turns out that if you're in this large depth regime, that the spectrum doesn't depend on the details of the data at all. Or if you normalize the data points to have the same variance, the spectrum doesn't depend on it. So this is kind of a universal quantity that depends only on the hyperparameters of the architecture. And here's just a caricature of how those hyperparameters affect the spectrum. And I'm saying that if you use this special combination with orthogonal and weight variance that's small, you're on the critical line down here. You satisfies all these conditions, then the Jacobian will have a shape that concentrates near 1, even for very, very, very large depth. And if you use those initialization protocols to train models on MNIST and CFAR10, then you are able to effectively train these enormously deep models without any kind of degradation in terms of training or test performance as you increase the depth.
So you're saying this is how to choose random initialization?
Absolutely. Exactly. So far, all I've talked about is the prior. And just by characterizing properties of these macroscopic observables, one can have a pretty strong empirical effect on practice, I guess. But you're right that there's a big gap here between the prior over functions and what happens during the course of gradient descent. And that's just left unanswered at this point.
It seems that dynamical isometry calculation is based on fully connected.
Yeah.
And I'm wondering for convolutional analysis to do experiments, so what would change?
We did the calculation in that case too. It's somewhat more complicated. You need to know how to initialize an orthogonal convolutional kernel, which is also somewhat complicated. And there's some additional subtlety there. I didn't want to get into all the details here, but you can work through it all. And the result of that work is that you can train these deep conv nets.
So do you see a benefit of having very deep networks on these tests?
No. No. This is one of the motivations for pursuing this analysis, in fact, was there had been a trend a few years ago where like deeper residual networks, for example, 1,000-layer ResNet was sort of state-of-the-art for a while. And we were thinking, well, okay, is depth really buying you anything in terms of representational power? There's a better inductive bias. Can we disentangle some of the components of the residual architecture from the depth? And well, we pulled out all the components except the depth, and it didn't help.
Were these empirical results that you presented, can you give us a sense as to how far you deviate from your visualization?
Oh, pretty far, yeah.
The initialization that someone might naively do, like how can you characterize what it's going to look different? How much more subtle this is and how much better it is?
Yeah, it would be nice to have a plot, but I basically what you would see is just chance performance at every step. If you're at 4,000 layers, if you're at 50 layers and you use a naive initialization, you're going to get chance performance. I mean, it depends a bit on the architecture. Like with ResNets and with skip connections, you can get pretty far. But for these vanilla feed-forward models, yeah, I think you sort of cap out in the dozens. Okay, so should I continue on? I guess we're over time. We're fine? Great. Oh, okay, perfect. Great. So up until now, I've been talking about, again, the prior over functions and what one can say about the macroscopic observables at initialization. And I think, in the next lecture or two in this course, you're going to hear quite a bit more about how over-parametrized models evolve with gradient descent, and probably hear it in great detail. So here, I would like to just give a more intuitive motivation for what I think is really the striking result here, which is that very, very wide neural networks evolve as if they were linear models. So what's the intuition here? So let's say we have the class of models we've been considering so far, just a fully connected deep model. The parameters theta are dependent on the time. And I think many of you, if you've gotten your hands dirty playing with big neural nets, have perhaps noticed empirically that if you increase the width of your model, the parameters end up moving less and less during the course of training. And by that I mean the individual parameter values themselves move less and less. So this is an empirical phenomenon, which has subsequently been backed up by very detailed analysis. And if this is the case, then naturally one can just consider expanding the function at time t around its value at time 0. And it turns out, and the magic is all here, which I'm not going to explain in detail, that as the width goes to infinity, truncating this expansion at first order is actually exact. Now, the exactness of this depends on a number of assumptions, how you've initialized things. The learning rate is small enough, and many, many, many caveats. But for the types of things I've been talking about up until now, this is in fact true. And I should emphasize that the Jacobian here is time independent. It's just the Jacobian at initialization. And it's different Jacobian than what I was talking about a second ago. It's the derivative of the output of the model with respect to the parameters, not with respect to the inputs. This is the output parameter Jacobian. And it's a constant matrix that you could compute at init. And given that, what you have for the time evolution is just a linear model. So many of you, I guess, have probably heard of this result, but if you haven't, I think this should be pretty surprising. And to us, we really wanted to do a thorough empirical investigation. So here's some results in that direction. Here we have, on the x-axis of each panel is gradient descent time. The solid lines are the fully nonlinear neural net. The dashed lines are these linear model first order approximations. And the y-axis and the different panels are just different metrics measuring how closely the quantity agrees over the course of time. For example, in the top left panel, we look at, 10 or so different training points and ask what value the model predicts as output for those points at various times. And similarly, in the center top for test, and those agree very well. The loss and accuracy as a function of time match very well. So this is for fully connected model with 2000 with MSE loss. You could do the same thing for slightly narrower. Here's with 1000. Now this is cross entropy loss with momentum. Also excellent agreement. You do CNNs. They also agree well.
How do you calculate the linearized model? Do you run like a quadratic optimization problem, or do you just
No, what we're literally doing is defining a model to optimize that is exactly this equation, and the dynamical variables are omega, and then we just run gradient descent on this. So we can also look at residual nets, res nets. We see good agreement here as well. So you may have noticed that towards large time on these plots, they begin to get some deviation. And yeah, that's fairly well understood. That's expected to happen. The question is, how far can you go in time before the deviation kicks in? That depends on the width. And for finite width, it happens sometime. OK, so the empirical evidence, at least for certain classes of models, is that this linearization perspective is correct. I mentioned before that it does break down in some cases, and I think you'll probably hear some about that breakdown maybe in the next lecture or two. So I want to just, though, bring things back to the discussion of the posterior over functions. So if you believe that this linearization perspective is true, then you have just a linear model, which you can solve analytically. The solution involves what's known as the neural tangent kernel, which is just the Jacobian times its transpose. And in terms of that kernel, you can solve the differential equation analytically and actually write down what the prediction will be, mu, at any test point x, little x. And it's given in terms of this kernel theta. And, sorry, this is for MSE, of course. But you can do more than that because the posterior over functions is actually a Gaussian process. So you can specify the mean of that Gaussian process as mu, but you can also compute the variance or covariance. And that's expressible in terms of this neural tangent kernel and in terms of the NNGP kernel K that I was calling sigma before. So the posterior is a Gaussian process, and you can specify everything there is to know about it. And again, the randomness here in this Gaussian process comes from the randomness at init. So here's just a visualization of the distribution over functions that you learn in some simple 1D case. So the training points are the dots, basically, and the envelopes are the kind of, I think, one sigma bands that sort of define the distribution over predictive functions. Okay, so actually that's all I have to say. I would like to just emphasize that over-parameterized models become very, very simple. You know, I showed you how you can compute the prior analytically and how properties of that prior can inform design decisions like hyperparameter optimization if you have a deep network, for example. And I argued that wide neural nets are basically linear models in some cases. But overall, the main point that I would like to make is that by considering these very complex interacting systems in the right way, one can come up with macroscopic quantities that can really shed a lot of theoretical insight into the problem. So I'll stop there. Thank you so much.
Any question?
Just try to clarify that. So for the dynamics of the covariance, so it's not that it's bad because it's going to a fixed point. It's because the fixed point, like the covariance is really degenerating at the end. That's what you don't want. And you sort of want the dimensionality of the final covariance to somehow match that of the possibly, or something. I don't know what I'm talking about.
Yeah, I mean, I think that basically characterizes the intuition. It's that the fixed point is degenerate and informationless. That's the problem. Yeah.
Other question?
It seems that you have an approximation that predicts what the function is going to be run with gradient descent. So could you use this as an alternative to doing gradient descent? And would it be more efficient computationally to do gradient descent?
For small data sets, it might be more efficient. But I mean, one way of looking at this is just a particular kind of kernel method. So for any problem that you might attempt to apply some kind of kernel method to, this could be one way of defining the kernel. In fact, I think there has been some recent work showing that for certain kinds of image classification tasks, for example, that the kernels induced by some convolutional architectures really do drastically outperform the types of kernels people might typically use, like RBF or whatever. But I think for large data sets, you know, I mean, you have to you know, effectively invert a giant matrix. And of course, then you're really only getting savings with the analytical result in the NSE case. And, I mean, there's lots of computational challenges.
Other question?
So you use the word prior and posterior space spaces, and I guess posterior is not equivalent to say put the prior of the base to be Gaussian and compute observe data and compute the posterior of
Yeah.
the base. It's
Yeah.
not the same as
That's correct. Yeah.
it's another sense of posterior.
So in the case of, yes, absolutely correct. It's posterior only in the sense of that's the distribution of functions you learn post-training. It's not posterior of a probabilistic inference.
Yeah, I'm wondering what's happening in the, is that the chaotic regime completely useless, or we don't know how to use that method?
I guess I might say that it's probably pretty useless, but maybe the jury's still out a little bit. So I'm not sure. Things can. It's whether or not. I mean, if you haven't converged identically to the fixed point, then you're just close to it within some numerical precision. And the problem is if the computations you perform have some precision loss that's around the same order, then you're just going to get kind of noise. But I guess with arbitrary high precision, maybe there's no problem anywhere. So I don't know if that answers your question.
To show the deviations from the linear model of the last session, so that's probably better, right? Because otherwise it would just be equivalent to a kernel method. So you say that the linear regime is explaining some part of the training, but real networks with more complicated data where the final output is not just replicating a kernel, that you care more about what's happening in the stats.
Possibly. I think I would actually say the jury is maybe still out about whether or not some kernel methods could in fact outperform and whether these linearized models might actually be better in some cases. But I guess our empirical evidence has been exactly what you said, that typically the nonlinear one does start outperforming when they begin deviating. And furthermore, there's an upshot to this that's positive, which is that if we know that when the nonlinear model starts deviating, its deviations are good for generalization, then that gives you some kind of delta to focus on in terms of where the good generalization is coming from. So that could be worth looking into for sure.
I want to ask two questions about like deviating from your model assumption. One is you assume that all the hidden layers are having the same, and so I'm wondering if you have a different NI where say constant ratio to each other, like alpha I to bigger.
Yeah. We haven't pushed that. I don't think it ends up giving a qualitative difference to anything in this regime. I think it might start mattering when the data set is also large to take into account these rectangularity factors. We haven't pushed through the analysis in the general case, but you could do it. I don't think it has a big effect.
And also, like, you have a lot of like empirical evidence for like residual net. So I'm wondering for the theoretical part, the like ResNet give you much looser.
Yeah, the problem is batch norm, complicating the analysis a lot. And the ResNets without batch norm just don't perform well. So we haven't really cracked that case yet.